In this talk, we're going to introduce the Vision Programming Interface, or VPI, which is NVIDIA's newest computer vision and image processing library. It is designed to enable programming of efficient computer vision pipelines, taking advantage of several computer engines available on Jetson devices, and also on x86 architectures with the NVIDIA GPU. So here's the agenda for today. We'll start off answering the question, why use VPI? Then we're going to go through the core concepts you need to know to use the library efficiently. And in the next section, we're going to use those concepts to build a stereo disparity estimation pipeline whose results are shown in the picture. It takes two images left and right and outputs an estimation of the pixel disparity between them, which is related to the scene depth. And at the end, we're going to present some features planned for the future to get you an idea of where the library is heading to. And lastly, we're going to have a Q&A session. So if you have any questions in the course of the talk, you can either save it up and ask at the end or use the Q&A box. So here you go. Why use VPI? Let's talk first about the current solutions available. So say you have to implement a computer vision solution, right, that runs on different compute engines. You would pick a number of libraries, right, to interface with those compute engines. And the problem is that those libraries are usually mutually incompatible, so it's hard to make them work together in a single solution. For instance, the memory management can be hard to get right. Say you have this memory buffer on CPU and you have to access that on the GPU, and you want to minimize or even to avoid altogether any kind of memory copying. The resulting code can be difficult to experiment with or to fine-tune. You have to touch several knobs and touch the code in several places in order to optimize it. And to make matters worse, some compute engines might not even be directly accessible via public API. So we can see here this Jetson device, has several compute engines, PVA, VIC, but they are not directly accessible, so you cannot use them in your solution, at least not in a direct way. The Vision Program Interface aims at solving those problems. It allows you to create efficient computer vision pipelines that use all Jetson embedded accelerators. So one unique aspect of VPI is that each algorithm is implemented by several different accelerators, allowing you to easily do load balancing. So say your CV pipeline has multiple stages that are using the GPU, only using the GPU, and you have other engines that are idle. So using VPI, you can easily offload some of those tasks that run on GPU to one of those engines that are idle. Because the implementation of each algorithm yields similar results no matter what engine it runs into, the end result of your pipeline wouldn't change. And all the details regarding memory management are transparently dealt with. So you don't have to worry where the memory is, say CPU, GPU, BVA, doesn't matter. VPI will efficiently handle that for you using zero-copy techniques to make it available to different engines, provided that the memory characteristics are right and the compute engines allows it. VPI also provides interoperability with several known libraries such as OpenCV, Cuda, EGL, among others. This makes it easy to update existing code to use VPI. And lastly, VPI is designed to supersede NVIDIA VisionWorks. Programs that are using it are urged to switch to VPI, with the added possibility of using more compute engines other than GPU. Another significant aspect of VPI is its performance. So in this log chart, we can see how the CPU implementation of a number of algorithms in VPI compares to OpenCV. Separable convolution, for instance, is 30 times faster. Convolution is almost 20, and so forth. There are some algorithms that still underperform, but we are working to get them to the same performance level as the others. In this chart here, we're comparing the GPU performance of VPI against OpenCV using OpenCV's Cuda implementation. So in this case here, we can get up to 15 times faster performance. That's the case with convolution, right? Other algorithms are around 4 times faster. We have one outlier here, the FFT, that underperforms, but we are working on that one to get it up to speed. Lastly, in this chart, we are comparing the GPU performance of Vpi against VisionWorks on using Cuda. And here we can see that Vpi can get up to 6 times faster performance. That's the case with the Harris corner detection. And convolution is also not behind, 5 times. The other algorithms are, match VisionWorks performance, with the exception of convert image format that underperforms, but we're also working on that. Okay, so in this session, let's take a deep dive into the core concepts behind Vpi. So here are the 6 main components of Vpi. First, there is the backends that represent the compute engines available. Then there are the buffers, images, pyramids, and arrays. They represent the data. And of course, the algorithms that will operate on the data, like Gaussian filters, stereo disparity, and so forth. There's this concept of a stream that is basically an execution queue, so that algorithms can be executed in sequence. Finally, there's the events that are used for synchronization. So if you want different algorithms to execute in different engines in parallel, you can build more than one stream and synchronize them using events so that they all work towards the same goal. Finally, there's the concept of context. Context is used for resource management, but most of the time, you're going to be used the default context, so you don't even have to work with them directly. Vpi implicitly will use the default context. Here's how these components fit together. This is actually a good model to have in mind while working with Vpi. In the center, we have the processing pipeline. It takes the input buffers, does some operations on them, and write the results into output buffers. The processing pipeline is composed by one or more streams, each of them executing algorithms in sequence. Multiple streams are then used to execute algorithms in parallel. This is quite useful if the problem to be solved has internal parallelizable stages. Events are then used as synchronization objects between streams so that they all work together towards a common goal. Another way to think of pipelines is as a processing graph, where each node, the gray boxes in the figure, is an algorithm instance or an operation. The edges represent how the output of one algorithm is fed as input to another. So in this context, streams and events impose the correct sequencing of operations. So we can see here also that each algorithm task is executed by 1 to 4 available backends: CPU, Cuda, PVA, and VIC. Let's talk more about each one of them in the next slides. In Vpi, a backend represents one compute engine. Some backends are best suited for certain kind of processing tasks than others and have different performance characteristics. The Jetson AGX Xavier shown here, for instance, comes with all 4 supported backends. Depending on the problem, work can be split between all these backends, resulting in efficient utilization of all available compute resources. Desktop x86 PC, on the other hand, has 2, the Cuda and the CPU backends. Cuda here representing the GPU. Well, first let's talk about the well-known CPU backend. We tend to think that CPU is slower than GPU or other engines, and indeed it is. But if these engines are already busy while the CPU is idle, well, you're kind of underutilizing your system, right? That's the case shown here in the chart. The Cuda and the PVA backends are busy, and we are using the CPU that would be otherwise idle to run the Harris corner detection. In any case, the Vpi CPU implementation of several algorithms are quite performant, making it as a good contender. Moreover, the Vpi CPU algorithm implementations are multi-threaded. It benefits from CPUs with multiple cores, reducing processing time drastically. The CPU backend is available on both Jetson AR64 and x86 architectures. The Cuda backend represents the GPU in the system and is usually chosen when speed is a must. VPI's Cuda implementations are quite flexible, supporting features that other backends might not support, such as some specialized image formats or a broader selection of image border extension types. VPI supports several NVIDIA GPU architectures from Maxwell to Ampere on both Jetson devices and x86 architectures. The PVA, short for Programmable Vision Accelerator, is a power-efficient engine that is specialized to tackle some important computer vision tasks, such as the ones shown here. It is available on Jetson AGX Xavier and Jetson Xavier NX devices. Each PVA engine comprises of 4 independent vector processing engines, allowing increasing parallelism possibilities. Although not as fast as the Cuda backend, it's a good choice for applications that need power efficiency, or to free up the GPU for other tasks. The VIC backend represents the video image compositor presented on all Jetson devices. It is a fixed function engine specialized in video processing. It has low power usage and, like PVA, can be used when there is a requirement. Some algorithms, such as the perspective warp and the remap shown here, are only available on Jetson AGX Xavier and Jetson Xavier NX devices. Other operations, such as temporal noise reduction or image format conversions, are available on all Jetson devices. With backends understood, let's cover now Vpi Buffers. They represent 3 types of data: images, image pyramids, and arrays. Let's talk now about images. So in VPI, they are represented by Vpi image objects. As you would expect, images are characterized by their dimensions, image format, whether it's RGB, NV12, U8 for 8-bit inside, this one typically used for grayscale data. And most importantly, images are characterized by what backends can use them. This is actually a common theme in VPI. Several components require the user to define which backends will end up using them. This allows VPI to optimize resource allocation only for the backends needed. Here's a small example of how Vpi image can be used. On line 1, we declare a variable that will store the Vpi handle created on line 2. This call will create a 512 by 256 RGB8 image to be used by the CPU and Cuda backends. The variable that stores the handle to the created image is passed then as last parameter. Here, we are explicitly passing 2 backends in image flags parameter. There are situations, however, where you are testing some load balancing scenarios. You don't know a priori which backend will use a particular image object. In a case like that, it is often convenient to enable all backends at once. You can do it by passing 0 as image flags, or at least guarantee that no backend flags are passed. Once you're finished using the image, you can call Vpi Image Destroy on the handle. From there on, the image object cannot be used anymore. Vpi also allows you to wrap a memory buffer allocated elsewhere, so that it can be used as either input or output of pipelines. Currently, Vpi supports wrapping of OpenCV, Cuda memory, CPU or host memory, EGL image, and NV buffers. The last 2 only available on Jetson devices. So here, we'll show here how we will go about wrapping an OpenCV matrix. Line 1 loads an image from disk and stores it in the CV map. Then, on line 3, we pass it as a first parameter to Vpi Image Create OpenCVMat Wrapper function. Then, we pass the backends that are going to use it. And finally, the variable that stores the created Vpi image handle. From there on, the Vpi image can be used as any other image. Vpi will handle automatically the memory management operations to make the OpenCV memory accessible to Cuda when needed. This particular wrapping call infers the Vpi image format from some CVMAT characteristics. In this case here, 3 8-bit channels are understood to be BGR8, a common pattern adopted by OpenCV. There is an overload of this function that accepts explicit image format. Vpi in this case will check if this format is consistent with the CVMAT characteristics, return an error if it isn't. Line 6 here shows you how to make the Vpi image point to another CVMAT, provided that it has the same dimensions and format of the original image. That's quite useful in the main processing loop of an application, where the input images change at every iteration. By reusing the Vpi image, you'll avoid allocating memory all the time and setting up other image resources, speeding things up considerably. As usual, once the Vpi image isn't needed anymore, you just destroy it. But there is one thing to notice here is that the CV mat must not be destroyed while there is a Vpi image wrap in it. Failure to do so will lead to undefined behavior. Most likely your program will crash sooner or later. In this example here, we wrap a Cuda memory block, such as the ones allocated by Cuda malloc pitch function. In this case, the syntax is a little bit more complex, but not too much. In lines from 5 to 11, we fill the Vpi image data struct with the information we know about the Cuda memory, such as the format, number of planes, number of bytes in a row, the so-called pitch, dimensions, width, height, and the pointer to the memory, etc. We pass that to the Vpi image create Cuda memp wrapper function, and like we did the OpenCV wrapping, we define the backend that we're gonna access it. On line 16, we use the Vpi set wrapped Cuda mem function to redefine the wrapped Cuda memory buffer. Again here, the new buffer must have the same characteristics of the original one. The rest of the code is what you expect. You use the image and then destroy it. Note that we are freeing the Cuda memory only after we destroy the Vpi image that's wrapping it. Here we have the image pyramids, and it's basically what is shown here, a list of images of different dimensions. Those images are somehow related to one another. This is quite useful in algorithms like the QLT feature tracker or any other that use image pyramids as an optimization. We are, however, not going to explore image pyramids in this talk because they are not needed for the stereo disparity estimation example we're going to show later today. You can check the VPI documentation in order to learn more about them. Finally, VPI supports 1D arrays. They're used to store, for instance, the key points extracted from an image by the Harris-Corners algorithm shown here. Or maybe bounding boxes used in QLT template tracker. Again, we are not going to delve into arrays in this talk as they are not used in the stereo example. Well, buffers are only part of the story. They are kind of useless without algorithms to operate on them. So, in VPI, an algorithm represents a well-defined computation of buffers. So, as you can see here in the table, each algorithm is implemented by several backends. These implementations are equivalent in the sense that, given the same input, the output of each implementation is functionally the same. Some small variations are to be expected since, for instance, some backends work with fixed point math while others use floating point or other optimization strategies. Such differences don't change the mathematical meaning of the result. An application that depends on bit exactness of the algorithm's output are most of the time ill-posed or not robust enough. VPI offers a good selection of algorithms, ranging from basic operations such as convolution or image rescaling, to more complex ones like pyramidal, L-key optical flow, QLT feature tracker, or temporal noise reduction. VPIs make it quite easy to switch an algorithm to be executed in a different backend, as we're going to see in the next slide. Let's analyze some algorithm calls. Here we have two. Box filter operation on line 1, followed by the image rescaling on line 4. The box filter call will enqueue the filtering operation in the stream passed as the first parameter. The second parameter defines which backend will execute it. You can change the backend by simply changing the enum. The 3x3 box filter will operate on image input and write the blurry result on the image temp using the clamp border extension type. Then, on line 4, we use the rescale operation to change the dimensions of the blurred image, rescaling the content accordingly. The result is written to image result, which was created with the desired destination dimensions. It will also use the clamp border extension. So, submitting the two algorithms in the same stream ensures that they will be executed in sequence. This is made clear here as the output of the box filter is used as input of the rescaling operation. Note that the algorithm submit calls are asynchronous. That is, the control returns to the calling thread as soon as the operation is pushed into the queue for execution. It doesn't wait for the algorithm to be executed. This leaves the CPU free to perform other tasks. So the previous algorithms were quite simple. They don't need any auxiliary resources to do their thing. But that's not the case with some other algorithms such as the stereo disparity estimator as shown here. The resources they need are encapsulated in the VPI payload object. So in general, algorithms that have payloads are handled similarly. The user is responsible for managing its lifetime. First, you call a function that will create the payload. Then you submit the algorithm to a stream along with the payload and other parameters. When the payload is not needed anymore, you just destroy it. The same payload can be used in multiple algorithm instances sent to the same or different streams. You must only ensure that this payload object is not used concurrently in different streams, otherwise your program might crash. Finally, when no stream is using the payload or will ever use it, you're allowed to destroy it. In the example shown here on line 2, the payload for the stereo disparity estimator is created. You then pass which backend will execute the algorithm, then all parameters needed for auxiliary resources allocation. In this case, you need the input image dimensions and the image format. The left parameter receives the VPI payload handle. On line 6 to 8, structure is filled with some additional parameters this particular submit function needs, like the maximum disparity or the search window size. Finally, on line 10, the stereo disparity estimator is submitted to the stream to be executed by the PVA backend. The respective payload is sent along with the input stereo pair, the left and right images, and the VPI image where the calculated pixel disparity will be written to. The parameter structure we filled just then is passed as last parameter. Again, this submit call is asynchronous. Once we're certain that the processing has finished, and we'll see that in a minute how it's done, we can destroy the payload. This will deallocate all auxiliary resources. Now let's get to the components that are used to effectively create the processing pipeline structure. The main building block we're going to use here is the VPI stream. As we've seen when talking about algorithms, the stream is where they are submitted to for execution by a backend. It represents a task queue where tasks are executed in the order they are submitted. The figure here shows how it works. Tasks are submitted at the top and executed by a backend at the bottom. Upon submission, the algorithm is associated with the backend, as we've seen previously. Upon execution, the stream knows which backend to dispatch the algorithm to. Moreover, streams allow for asynchronous algorithm execution, as we've said a couple of times now. You submit the algorithm and don't necessarily wait for its execution, meaning that the submission is a non-blocking call, at least most of the time. Only when the stream is full, the submission call blocks until there is a free slot. Currently, the stream has a capacity of 64 in-queue tasks. However, in practice, this limit is rarely reached, meaning that the calling thread can continue assembling the pipeline while the algorithm submitted so far execute in parallel. Now let's go into some more interesting problems. If the pipeline at hand allows for some processing stages to be executed in parallel, you can create multiple streams, one for each parallel branch. Internally, every stream is associated with a CPU thread that processes the queue independently. In a case like these, you almost surely need to use VPI events to synchronize streams with each other so that the ensemble works together in coordination towards the same goal. We're going to talk about VPI events in more detail shortly. Finally, when the work is over and the stream is not needed anymore, it can be destroyed. The destruction call will block until the stream is empty, meaning that all algorithms have been executed. Now onto how that looks like in code. Line 2 creates a brand new stream that can dispatch algorithms to Cuda, BVA, and Vic backends. Similarly to buffers, for optimal performance, you want to restrict the stream to only the backends that are going to be used. The last parameter is the VPI stream variable that receives the handle to the created stream. Then, on line 5, we submit a 3x3 box filter to the stream to be executed by the Cuda backend. This call will return immediately. Then on line 8, a rescale algorithm is submitted to be executed on Vic. So from now on, since we don't have anything else to do, the whole pipeline is set up. We just wait for it to finish execution. On line 12, we call VPI stream sync on the stream. This call will make the calling thread wait until all work submitted to the stream is finished. After that, we're safe to destroy the stream on line 13. The ones out there who are Cuda programmers might have already noticed that VPI streams are surprisingly similar to Cuda streams, and this is no coincidence. Algorithm submission is the equivalent of a Cuda kernel submission. You eventually have to wait for them to finish to use the results, so nothing radically new here. Finally, Vpi Event Handling. I've talked before about the parallelization possibilities arising from using multiple streams. That's what I'm showing here. In the bottom left corner, we have this pipeline we want to implement. It starts with 3 parallel stages whose result is fed into algo 4. Somehow, algo 4 must wait until the results are ready. VPI events allow exactly that. On the larger figure, we depict in blue the host thread, from where the algorithms are submitted, and in yellow, the pipeline, which is 3 streams. So, the first thing we do is set up stream 1. First, we submit algo 1, and then submit the event task that gets signal when it reaches to the bottom. We then do the same for stream 2, but this time submitting algo 2 and event 2. Lastly, we work on stream 3. First, we submit algo 3, but then we have to submit event wait operations for inter-stream synchronization. When these operations get to the bottom, they'll block the stream execution until the corresponding event is signaled. Note that the host thread that submits the event wait operation doesn't get blocked. All calls are still asynchronous. Finally, we submit algo 4. The net result is that algo 4 will only execute once algo 1, 2, and naturally algo 3 are finished. The last thing the host thread does is a VPI stream sync call on stream 3. This effectively translates into submitting an event signal operation to it, and have the calling thread wait until it's signaled. By the time this happens, all algorithms are sure to have been executed. Another way to think of events is that they record the stream state at the moment it is submitted. So for instance, when signal event 3 is submitted to stream 3, it records all operations that are queued and have not been executed yet. Here, all 5 operations in stream 3 are recorded, since none of them were executed yet. When they're all done, event 3 will be signaled, and the host thread that was blocked until now can resume. Here's how this pipeline translates into code. On lines 2 and 3, we create 2 VPI event objects. For simplicity, we pass 0 as event flags, meaning that the event is enabled for all available backends. Then, on line 4, we start setting up stream 1 by submitting the box filter algorithm and record the stream state on event 1. On line 6, we do the same for stream 2. Just submit a box filter operation and record the stream state on event 2. Finally, on line 8, we set up stream 3. First, we submit algo 3. The convolution operation, and then on lines 9 and 10 we use VPI stream wait event function to make stream 3 wait for the tasks recorded on events 1 and 2 to complete. Then finally we submit the final algo 4, the KLT feature tracker algorithm that depends on algos 1, 2, and 3 outputs. After we finish assembling the pipeline, on line 12 we wait until stream 3 is idle. And on lines 13 and 14, we destroy the events, since we don't need them anymore. Again, that's all quite similar to how Cuda events work. Well, so far we're assuming that life is good, calls never fail, etc. But that's often not the case. That's when the topic of error handling is important. Almost all VPI functions return a VPI status code indicating either success or failure. For instance, on line 2 here, we are trying to create an image with a negative width. This obviously fails. Line 4, we test the status code. If it is not VPI success, that means a failure, and we have the option to get a more detailed error message using the VPI get last status message call on line 8, then printed on stdout. Functions like VPI get last status message, or VPI get last status, or even VPI peak last status work on the status reported by the last VPI function executed by the calling thread. The functions that start with VPI get last status will return it and reset the internal status value associated with the calling thread. On the other hand, VPI peak last status will just return the associated status and not reset it. Errors on algorithms that are executed asynchronously are only passed to the application when the stream or the event sync function is called, or when a new task is submitted to the stream. Each stream has its own error state. This state is reset when the error is transferred to the host calling thread. Now let's take a look at the big picture, how your VPI-based program should ideally be structured in order to get the most performance out of VPI, while also adhering to some of the best practices in software design. You should divide your program into 3 stages. First is an initialization phase that happens once the program starts. That's where you allocate all resources you need: images, streams, events, payloads, etc. With that done, the main processing starts. Ideally here, you won't need to allocate memory. This effectively defines a high bound on the amount of memory your application will ever need. Then, still during the main processing, there is usually a loop that fetches input from somewhere, say a new video frame from a camera, then processes the data in a VPI pipeline, waits for the processing to finish, and consumes the result. Rinse and repeat. When the program ends, we do the cleanup, deallocating all resources allocated during initialization. As we saw before, the VPI API revolves around this concept of resource allocation, utilization, and destruction. This maps well with the program structure we are proposing here. Alright, that was a lot of information. Thank you for following so far. In this section, we'll put into practice everything we've learned up to now by coding a full stereo disparity estimation pipeline. The problem here is given a rectified stereo pair, basically 2 aligned images from left and right cameras, we want to recover the depth information in them. By aligned images, I mean that a point object shown in both images must be in the same row, no matter where the point is on the scene. The column difference of this point in both images is related to its depth in the scene, and that's the disparity we're looking for. The larger the difference, closer the point is to the camera. Disparity is also known as parallax. Note that the images straight from stereo cameras are usually not aligned. For that, you can use VPI's lens distortion correction procedure along with the camera calibration information to align them. This step isn't covered in this tutorial though. Please consult VPI's documentation for more information. VPI's stereo disparity estimation uses the semi-global matching algorithm, where the pixels on the left image are matched to the pixels on the right. Simply stated, for every pixel, it calculates the similarity of this pixel to all other pixels in the neighborhood in the other image, selecting the most similar. The resulting horizontal displacement is the pixel disparity that gets recorded in the output image. The actual depth can then be calculated from the disparity. But for simplicity, we'll only work here with disparity. You can see an example of the output in the image at the bottom. The algorithm isn't perfect though. Regular patterns or textures, or even occlusions, that's when one object is shown in one image but not in the other, gets the algorithm to return invalid information. There are ways to handle that, but it's out of the scope of this tutorial. Here's how the stereo pipeline looks like. Starting from the left and right rectified images, we first have a pre-processing stage where we downscale the images using Vic and convert them to grayscale using Cuda. This is done because PV's stereo disparity algorithm expects the input to be 480 by 270, 16-bit unsigned grayscale images. This pre-processing stage is run in parallel for both images. The grayscale images are then fed into the stereo disparity algorithm. The resulting disparity image needs some pre-processing before display though. Right now, they are in Q11.5 format. That's a fixed point precision format. We must convert it so that its range is 0 to 255, so that it fits in an 8-bit unsigned image. That's what we're doing here using Cuda's convert image format algorithm, which also converts the data range. We see here that the different backends work together towards the same goal. As you already know, we'll surely use Vpi events to make it happen. The first step in implementing the pipeline is decomposing it into streams. Since we have two parallel branches, that will translate into at least two Vpi streams, aptly named left and right streams. In the bottom left corner, we have our little cheat sheet that we'll use throughout this example to help us know where we are during implementation. The diagram also includes all intermediate images needed. In total, we'll need 8 Vpi images, 2 for input, 1 for output, and 5 intermediate images. In the diagram on the right, we define how our streams are set up. As usual, we read the execution sequence from bottom to top. At the beginning, both of them are used for pre-processing. Then, we reuse the left stream for the second half of the pipeline, where we execute the stereo summation and post-processing. We'll use one Vpi event object for inter-stream synchronization. We also know that the stereo disparity algorithm needs a payload. Well, with that said, we are ready to start rolling. First things first, include all headers we need. Then we start the initialization phase on lines 10 and 11, where we fetch initial stereo pair from OpenCV's CV video capture objects, one for each camera. We are assuming here that these images are already rectified. Then, on lines 13 and 15, we create the Vpi images that wrap them. From our cheat sheet, we know that these images are only be used by Vic, so we only enable the Vic backend on them. Note that obviously these images coming from CVMAT are also accessible by CPU. So in this case, the OpenCVMAT wrapper will automatically enable the CPU backend on these images. For simplicity, we are assuming that in-left and in-right's image format are accepted by the Vic downscaler. Next up is creating the intermediate images so that the input and output restrictions of PV's stereo disparity are dealt with. First, on line 2, we get in-left's image format. That's our left input. That's because on lines 4 and 7, we are locating the 480 by 270 versions of this input. The dimensions are different, but the format must be the same. Note that here we are assuming that the left and right images format are the same. Again, from the cheat sheet, the small left and right images will be accessed only by Vic and Cuda, so we enable only these backends on them. Then, on lines 11 and 14, we allocate the images that will store the grayscale versions. Same for 80 by 270 dimensions, but this time the image format is U16. That's a 16-bit unsigned format. Finally, on line 18, we allocate the image that will store the disparity that comes straight out of the PV algorithm. It writes it to a U16 image, but the data itself is in Q11.5 format. Since we'll set up the algorithm to return disparities from 0 to 63, this means that the output will range from 0 to 247, considering the binary fractional part. This image will be accessed by PV and Cuda, so the backends are set accordingly. Now on the output image. We want the Cuda range conversion to write directly into the OpenGL PBO, which is short for pixel buffer object that will be used for display. We'll have then to wrap it into a Vpi image. Lines 1 to 10 basically create this PBO and sets up the Cuda OpenCV interrupt function to retrieve a pointer to the PBO's data, accessible by Cuda. And then, as you recall, on lines 11 to 18, we'll fill up the Vpi image data with information about this buffer. The buffer here is 480 by 270 with a U8 format. Finally, we create the VPI image object that wraps this OpenGL PBO on line 20. Now we create the remaining objects. First, the stereo disparity payload is created on line 2, just like we did before. By default, the algorithm will return up to 64 disparities. Then, on lines 7 and 10, we create the left and right streams. The left stream will use the Vic, Cuda, and PVA backends, while the right stream will only use Vic and Cuda. At the end of line 12, we create the event object we will use. Okay, initialization is finished. On to the main processing. Here's how the main loop goes. Lines 1 and 2 fetch the stereo pair from the CV video capture objects. Then, lines 3 and 4, we redefine the wrapped VPI images to this new stereo pair. No resource allocation is done here. It's a quite efficient operation. Pre-processing starts on line 5. First, the rescale and convert image format algorithms are submitted to the left stream to be executed by the Vic and Cuda backends. We do the same for the right image on lines 10 and 13. Now we start the second half of the pipeline. We want the left stream to wait until the inputs to the stereo disparity are ready. For that, on line 1, we record the right stream state on the AbSync object. And on line 2, we make the left stream wait until all tasks on the right stream captured by the event finish execution. Of course, by the time the stereo disparity starts to run on the left stream, the left input will already be processed. On lines 3 to 5, we fill the VPI stereo disparity estimator parameter struct with some parameters that are needed by the algorithm. Here, we're using the search window of 5 by 5 pixels, and the maximum disparity return is 64. Actually, it's 0 to 63. Last, we submit the stereo disparity estimation algorithm to the left stream to be executed by PVA. Alright, we got the disparity data, but it needs some massaging before it gets displayed. That's where the post-processing kicks in. We'll use the convert image format for range mapping, from 0 to 2047 on a U16 image into 0 to 255 on a U8 image. When we do range conversions, we must first fill the VPI convert image format param struct with the scale that will be applied. So on line 2, we first initialize the struct, and the call will set some attributes to their default values. That's also always a good thing to do. Then on line 3, we define the scale correctly to map the range that we'll need. Finally, on line 7, we submit the algorithm to be run on a Cuda backend. This finishes our pipeline. Remember that the result will be written directly into OpenGL's PBO via a Cuda pointer that is wrapped by a VPI image. Because we don't have anything else to do on the host thread, on line 8, we synchronize the stream. The call will block until all operations previously submitted are finished. Only then the PBO can be displayed on screen. And that's it. This finishes one loop iteration. Now it will go back and process the next stereo pair from the camera until the user closes the application. When it's time to close the application, we must go through the cleanup phase. I recommend you to start off by destroying the streams. That's what we do on line 1. As I said before, the VPI stream destroy will wait until all operations submitted to the streams are finished. Think of this as a safety measure, because if you start destroying the images and an algorithm is still using it, or will use, your program will crash. Then we destroy the events, payloads, and all the VPI images. Note that we destroy the wrapped PBO only at the end, after all VPI images are destroyed. The CV mat will be destroyed when their destructures are called. In the next slide, we'll see a video of the pipeline we created together in action. So here's the pipeline we've just created in action on a Jetson AGX Xavier, which has a PVA engine. On the left, we have the stereo pair, left on top and right on bottom. On the right is the corresponding stereo disparity. The darker it is, smaller is the disparity, meaning that deeper that region is. On the bottom status bar on the right side, we can see that this pipeline is taking around 18 milliseconds to complete. here that because the sky region is featureless, the algorithm outputs invalid values for disparity, as I've mentioned previously. VPI's documentation states that PVA's stereo disparity algorithm takes around 14 milliseconds to complete on a 480 by 270.
We're almost at the end of the talk. It's time for us now to go through some of the features that are being considered for VPI in the future. We want to add batching and tensor support so that VPI can be used for some specialized pre- and post-processing operations required by deep learning inferencing pipelines. Also, as it is clear now, VPI currently is a pure C API. We want to create a Python API on top of it so that VPI can be used in a more diverse environment. You'll be able to code your VPI pipelines directly in Python using an interface that is in some ways simpler to use and to experiment with. This also applies for C++. VPI will make use of several C++ capabilities to make the library more expressible, safer, and easier to use. Currently, VPI lacks pointwise operation on buffers. Things like the power function, multiplication of two images content, sine, cosine, threshold operation, etc. These operations, if implemented naively, lead to poor performance due to increased memory I/O operations in relation to the actual computation performed. So to solve that, we are planning to add algorithm fusion, where a sequence of pointwise operations are all fused together so that the image is read and written only once. There are plans for more feature detectors, extractors, and matchers. And finally, an accurate end-to-end color handling for applications where color fidelity is important. Now it's time for the QA section, where we'll answer the questions you might have. Hello, here's Rodolfo, and thank you once again for joining us. I hope it was informative. I have here some questions that I want to address. For instance, does VPI have a graph facility similar to Cuda graphs? And the answer is currently no, but the public API was designed to allow that extension in the future. It's just that we didn't have a need to do that currently. But, you know, who knows? Another question, and I'll ask David, is also our engineer, and there is, just a second, does VPI dynamically switch between backends depending on measured load, or only specified by the user at compile runtime?
Right, so as you discussed in the presentation, the scheduling in VPI is static, so at the submission time you have to specify which backends you plan to run. We don't do anything smart. It kind of goes beyond the scope of what VPI is doing right now. To do it right, you would need to know, future and the entire system load. So scheduling, dynamic scheduling is a very hard problem, but what we allow people to do is to basically specify and load balance their own pipeline manually. They can either do it by trial and error, or they can use the documentation that's available online. So we document the performance numbers for all the backends, all the algorithms, typical use cases. So usually, you can relatively well come up with a pipeline that's kind of using all the hardware equally well and getting maximum throughput without much hassle. That's in pretty much user's control.
Okay, thank you, David. I have one more question here, and I'll handle this one. Can VPI streams be tied to Cuda streams? And the answer is yes. Actually, we have functions that wrap a Cuda stream, so that is used internally so that you can submit VPI algorithms to that Cuda stream. Just you have to be aware that while doing that, you have to make sure that the VPI has total control of that Cuda stream while the task reviewed and executed. So another question here for David. Why did you make a separate library instead of a new version of VisionWorks?
So VisionWorks it's not a library. It's a Vision SDK. It's a collection of libraries. Originally, even what we ship right now is basically a collection of kind of 3 different libraries. OpenVX is one. The other one is OpenCV, and the third one is kind of low-level implementation of OpenVX, which we originally called VPI. And when we initially looked at the problem, and the problem was to enable fixed function hardware in an efficient way that it allows to avoid copy and allow manual scheduling and asynchronous execution. None of those APIs could be built. So that's why we created basically this new Vpi API that addresses the problem in a holistic way.
Okay, thank you, David. I have another question here. I'll take that. Does OpenCV wrapping only work for CPU memory? So by CPU memory here, probably meaning CV maps. And the answer is currently yes. Currently we support only mapping. We have actually this utility function that maps CV maps into a Vpi image. But if you do have a CV Cuda matrix, you can get its pointer or and dimensions and the pitch and wrap it using the current Cuda wrapping facilities that Vpi has. It's just that we don't have this nice little function that can do that on one line, but it's something that we're considering adding. So one more question here for David. Element-wise operations like a square root, arctan2, scalar multiplication, square of a pixel value. So how to achieve canny edge detector?
Yeah, that's a good question. So the element, like VisionWorks API right now, OpenVX actually has immediate mode and also graph modes where you do have kind of pointwise operations, and you can smash together kind of pointwise equation that combines multiple of those operators. But the way it's implemented, each of those operators will map to a single kernel code internally. There's no form of fusion of jitting the code. And that maps to very inefficient code that's purely bandwidth bound, right? Our GPUs are very powerful. They have a very large ratio of compute to memory bandwidth. So we're by running addition, multiplication, division serially, we're severely underutilizing the hardware because GPU can compute much more versus the amount of data it can read in and read out, and every operator basically reads in the input and writes out the output. So that's kind of naive. So we decided consciously to delay pointwise operations in Vpi. So Vpi does not do trivial pointwise operations because we know we cannot implement it efficiently right now, right? And we didn't want to repeat the mistake of exposing individual kernels that implement pointwise operations. But there is a plan, and Rodolfo mentioned that in the slide 2, that we do have this in mind. It's a very useful feature, right? That you can have some weighting functions and just bake out equations. And so we do have a plan to add this feature in the future, but we'll do it right, which means we will have an API that allows you to basically specify the equation and series of pointwise operations in a way that will allow us internally to perform fusion and then potentially JIT code to create optimum kernels that map to this fixed function hardware or programmable hardware. That's the plan.
Okay, thank you, David. I have more questions here. Are there any plans? And I'll take on that. Is there any plans? Are there any plans for adding floating point support in Vpi? We do support floating point for some algorithms. For instance, the Fourier as transform, right? But floating point is not as implemented. There are not that many algorithms implementing that support, but we will consider adding in more because this is quite useful in some scenarios. Thank you for the question. Another question I have here, is Vpi already included in DeepStream? So Vpi is a separate library from DeepStream, so it installs independently. Actually, DeepStream uses internally Vpi, right? So you don't have to install DeepStream to use Vpi. It's independent. Get a couple more questions here. Why do you need, David, can you take on that? Why do you need to convert images in grayscale in stereo disparity or KLC tracker? Isn't it better to use RGB images?
Yes, this is a purely limitation of the implementation we have in VPI. So our implementation internally, especially the PVA1, is using grayscale as an input. It's true that using all three color channels would improve the disparity estimation a little bit, but that's what our implementation currently does. So if in the future, we see this as a kind of often requested feature, we might add support. Yeah.
Okay, thank you, David. Another question, I'll take on that. How can we stay updated about updates to VPI? So we do have our main documentation and our landing page. So on our landing page, you can probably search for NVIDIA VPI, and you easily get to our landing page where updates and more information are shown. And today we got a dev blog written about VPI, about the TNR algorithm, the noise reduction algorithm, that has more information about that. So that's something also easy to find online, right? So we are constantly updating more and more information about the project. I have some questions here about zero copy memory. So I'll take on that. So is wrapping data in VPI also zero copying? So for instance, data not duplicated on OpenCV and VPI? So the answer is it depends, right? Depending on the pitch, so the number of bytes in a row of this OpenCV memory, or the alignment of each row, we can indeed do zero copying. Like for instance, you can wrap a CV match, right, which lies on a CPU memory, and use it without any copies on a Cuda backend, a Cuda algorithm, or PVA or VIC. But in case that's not possible because of restrictions on the backend, we'll transparently do a copy, right, and act on the copy, and then copy the result back to the original buffer. I'm afraid we are reaching here the 1 hour mark. There are still questions here, but feel free to reach the Dev Talk forum to ask these and other questions there so that we can answer, right? Again, thank you again for the attendance. Publishing more webinars and dev blogs about VPI. Okay, thank you so much. Have a good day.